All right, so this talk is going to be a little bit confusing talk because we are living in a confusing time. That we hear that GPT-4 passed the bar exam. We have an existential risk, according to Yosha Bengio, while Yanukun says AI is not as smart as a dog. So literally everything, everywhere, all at once. Okay, so the talk plan is that I'm going to talk about the possible impossibilities of what appears to be sparks of AGI, and then talk about what appears to be impossible but might be possible if we try hard enough. That's going to include infinigram. And then discuss some paradoxes, such as the generative AI paradox. Okay, so starting with the first one. So AGI really seems to be around the corner, according to some people, but is there really anything impossible with these mighty transformers and language models? So I'm going to start briefly with this paper from NeurIPS last year about the limits of transformers on compositionality. Okay, so in particular, we wanted to see how well does GPT-4 does on multiplication. So we asked, how about multiply this number by that number? And it does give us some result that looks plausible, but it's slightly wrong. But of course, you heard that you have to ask it to think step by step. So then it does do that, and it's a different number now. It even have a trace of the computation, but it's still wrong. So, I was really curious, how well does this do, especially that, we hear amazing results from GPT-4, but I was really surprised that off the shelf, it does about 60% accuracy on 3-by-3-digit multiplication. In fact, if you ask larger digits, then the performance drops considerably. And this is kind of curious because once you know how to multiply numbers and then you have a pencil and paper, the number of digits shouldn't cause you to decrease your performance that sharply. But at this point, you might wonder why multiplication? We have better things to do this year, right? So in the paper, we also talk about or investigate other problems like dynamic programming or Einstein puzzles, which are types of different logical problems. But here, I'm going to just talk about multiplication because it's just like a straightforward problem to think about as an example of a compositional multi-step reasoning. And also to better understand what is possible and not possible. Is there anything impossible by any chance with the transformers? And by the way, I never imagined that I would actually give a serious scientific talk about multiplication in this year. But just, some people like the talk. I mean, the paper. Kevin Murphy liked our paper and others did, despite the fact that it's really about multiplication. And this is a little bit philosophical talk, by the way, so I'll make some points about why we looked at it later again. But we were curious, what if we do supervised training with tons of examples? So how many examples? 80% of 1.8 million examples. So this number comes from the fact that we're going to enumerate all the one by one. So on the bottom of the slide, we enumerate 1 by 1 digit, 2 by 1 digit, 2 by 2 digit, etc., until 4 by 2 digit, and then take 80% of them as training data and 10% to 10% for dev and test. So can you guess how well this might do if you train with GPT-3, largest model, 175 billion parameter model? So turns out it doesn't train so well. I would have thought that this should work better than this, but we got 55% accuracy. So, but of course, maybe there's some weird tokenization problem if you're familiar with this issue. So then we thought, how about we train GPT-2 from scratch only with 10 tokens? Maybe this should work. GPT-2 is much smaller, but being on academics, I cannot afford to train anything too big like GPT-3 myself, so bear with me. But what if we have only 10 tokens, 0, 1, 2, 3, whatever, and then with the correct tokenization with 80% of 1.8 million examples. That's a lot of examples, and GPT-2 XL has 1.5 billion parameters, so for the size of tokens, I think this is should be sufficient number of parameters. But to my big surprise, it didn't train very well. So we got only 10% accuracy for previously unseen examples of a 3x3 digit. By the way, it does memorize well on the training data, of course, but it's just that it doesn't really generalize well for the target task. Okay, so what about Scratchpad and step-by-step reasoning, and actually show this step-by-step reasoning trace and then do few-shot prompts with GPT-4. So turns out this does work really surprisingly well. The Scratchpad is very elaborate and long, so I cannot really fit that into the slide. But TLDR is that it does work so well. It's like 92% on 3x3. It's not 100%, that's curious. But if you stop your experiment here, you come away with this impression that, it almost works. But if you try 4x4, suddenly it doesn't work very well. Even with the Scratchpad, suddenly the accuracy is like 4%. This is really like stark difference from 92%. Okay, so what's going on? By the way, as we had this paper out, we got some complaint from Twitter that, wait a minute, that's the opposite of what this Google paper said, which said the teaching algorithmic reasoning through in-context learning is totally possible with, Scratchpad. So we opened this paper. It turns out it doesn't totally work. First of all, multiplication score rise from something really low, like 5.5% to 80%. So curiously, subtraction is worse. But if you actually look at the minor detail of the paper, they basically says that anything beyond the 3x3 digit doesn't work very well with the GPT-4. So what they did was, for any longer digit, they manually chop it into smaller digit multiplication and then add the results up by themselves. So it's like, this is not the same as just saying that, longer digit actually work with 80%. Because there's a lot of this, manual crafting going on. So in some sense, what the paper reports and what we report is the same thing, which is that there's some fundamental limits with the way that transformers may or may not be able to learn this type of multi-step reasoning. I'm not saying that nothing works. There are a lot of things that do work, but there's a limit, surprising limit, as to how much this can work. Okay, so we're just kind of crazy with this, so we wanted to see whether we can actually do supervised training of GPT-3 with the Scratchpad. So here's our price projection if you were to pay OpenAI API calls for 5x5 digit numbers. Then we only need $700 million that I don't have. I'm cheap. So we wasted about $8,000. Just because some people might still, I believe in GPT-3 or whatever, they believe in so much so that, they think this should work. So we did, just to see. And it turns out supervised training does work. I mean, this is not a news. So supervised training usually works for in-distribution data. But when you try larger digit numbers, then the performance drops sharply to 0 again. So, we did a lot of analysis in the paper. Let me give you some sketch of it. So basically, we looked at the computation graph of multiplication. By the way, there can be different types of computation graph. We don't know what transformers magically discover, of course, but let's look at just one version of it. So even with the 49/7 multiplication, you're actually doing fairly multi-step reasoning as a human. So we looked at this computation graph for many, many different multiplications, and here's what we found. Whenever a subgraph repeats a lot in the training data, that portion is likely to be correct. So it's almost as if instead of doing the full multi-step reasoning, there's this collapsed depth. So it's not like as multi-step as it may be, because these neural networks are very, very good at learning patterns and can collapse these multi-step to one step. So it doesn't mean that it's always correct for that portion, but we found that this highly correlates with partial correctness. We also have an appendix with some proof about how this is only as expected. Of course, with increasing multi-step, your performance naturally decreases. And in fact, our paper is not even the only paper out there that said deep neural networks can learn shortcut and fail to generalize as a result. But all these previous papers were not based on GPT-3 or 4. They were based generally on GPT-2 and smaller models. And then because of this extreme scale explosion, we found that a lot of people in the community kind of expect that with this large scale, there's sudden emergence such that now suddenly compositionality may be possible to master by these larger models. But we find that at least, to the extent that we experimented with GPT-3 and 4, it seems that these problems do not go away yet. Now, if you're a sensible person, of course you will ask me, why on the earth are you even doing multiplication? That's nonsense, because we should just use a calculator for that kind of stuff. And I totally agree with you. And there are some such models like tool formers. But the point of our work is not to say that we should do sequence-to-sequence models for multiplication, but rather to explore the possible limitations of these models, despite the fact that it just looks so mind-blowing good. And then also to ask another related question, which is for other aspects of compositionality, especially about certain kinds of language use or common sense reasoning, is it satisfactory, or does it seem correct that we're doing what we are doing currently, which is brute force a lot of examples to these sequential models? So, I don't really have an answer to this, but I just wanted to throw these questions to you because I think exciting recent results really open new intellectual questions about the potential fundamental limits of these transformers. Okay, but that's a bit too negative. I know that we should also do something more constructive. So let me tell you the impossible possibilities, which are about more constructive path toward building stuff. But I want to start with this quote from last year. So how can Indian startups create foundation models for India? Rajan asked, and Sam said, it's hopeless. Don't bother to compete with OpenAI. So in that context, is there something that seemed impossible, but maybe possible? So, I hope that Indian startups don't give up, first of all. Second of all, I don't have an direct answer to this, but just wanted to say that maybe we should try different recipes just in case. Okay, so I'm excited to share about this new work, InfoSum, or Information Theoretic Distillation, where we want to do summarization. So we want to learn to do summarization. And by the way, the winning recipe right now for summarization is to ask ChatGPT. That's the best thing, just prompt ChatGPT, or alternatively, do imitation learning from ChatGPT. So there's no other way except ChatGPT. That's, the current status quo right now. Okay, so that's what, some of the recent papers basically say. In that context, and also in the context of this recent paper from Berkeley that says the false promise of imitating proprietary large language models, which basically says that when you do imitation learning, you get worse model, okay? So all around it looks like there's no other way other than relying on ChatGPT. And even if you do imitation learning, you get something worse, right? Okay, so in that context, here's what appears to be impossible that I want to try. What if you start with very poor model? In our case, it's going to be Pythia from Eleuther, which is less than 3 billion parameter model. It's a good model, but it's like low quality compared to ChatGPT. It's small. Somehow do something so that we end up getting high quality small model. Okay, and then we go compete against ChatGPT on a task, summarization. We cannot compete on everything, but we're going to compete on summarization. So in order to do that, we're going to build on our previous work called the impossible distillation. So let me give you a brief summary of what our previous work was doing. So impossible distillation had this mission impossible. Learn to summarize sentences, not yet documents, but sentences, without extreme scale pre-training, without RLHF at scale, and without supervised data sets at scale. And by the way, this should be really impossible if you're, on top of NLP literature, as well as recent deep learning literature. It's like, this is impossible. But we have to have some advantage somewhere. We cannot have nothing, and then suddenly, out of nowhere, win over larger models. So our intuition is that AI is as good as the data it was trained on, okay? And by the way, any data on the internet, OpenAI already downloaded it. So the goal shouldn't be finding something somewhere on the internet. No, that's all gone. So AI, you have to synthesize data. Okay, so impossible distillation, we're gonna distill from GPT-2. To make it harder, we're not even gonna rely on ChatGPT. We're gonna start with the GPT-2. You remember GPT-2 that nobody talks about anymore? So do something with it, generate high quality data set, and that will enable us to train high quality model. But the thing is, if you try to synthesize summarization data from GPT-2, it's completely hopeless. So you give some prompt, like summarize the following sentence, and then give a sentence to summarize, and GPT-2 says nonsense back to you. So you try once, you try twice, you try hundreds times, and then you get zero good result, zero, almost like 0.1%, which is like as good as zero. Now what? So we had the prior work called the neurologic decoding, which can constrain your neural language model output space with some keywords. So, and this is plug and play inference time algorithm that you can just download any neural language models and put our neurologic decoding on top, and it can make sure that the output does include some keywords. So if we do that, then it's just slightly better. How much better? It's about 1% to good. So you try 100 examples, you get one good example. But this is not zero anymore. Now this is like something. And I thought this is as good as it can get, but students are just brilliant. Like the lead author, Jae-hoon, came up with this brilliant, where there's a will, there's a way, I guess. So, after studying GPT-2 behavior for a while, he had this intuition that just let it generate a sentence that it wants to summarize, and then let it summarize that sentence that it has generated. There's something about, what it just generated and then summarize that does lead to higher quality summary output. So, and then, skipping over the details a little bit, Jae-hoon and Peter together, they were able to increase the chance of success above 10%. Now, this is really, really big improvement. So what we do from here on is that we have this overall framework where you use GPT-2 to over-generate a lot of potential summarization candidate pairs, and then you filter that candidates aggressively because, it's only about 10% good. And the filter in our first work had these three, it's like water filter where there are multiple layers. Mostly it's not very important other than like we have this entailment filter on top, which is based on off-the-shelf model called for NLI. This is natural language inference classifier that can tell you whether something is entailed from something else or not. So a summary should be entailed from the original sentence or document. So we use, in this work, off-the-shelf NLI classifier in order to filter out potentially bad summaries. And of course, this off-the-shelf classifier is not very perfect, but by just over-generating and filtering aggressively, we were able to build high-quality summarization data set that OpenAI could not possibly download because this doesn't exist on the internet yet, and then be able to train GPT-2 on it. So that led to this model that was able to do better than GPT-3. And at that time, GPT-3 was the best model, by the way. Okay, now let's come back to our new work, which is Mission Impossible 2. So instead of summarizing sentences, now we want to summarize documents. This is much tall order. And now we are going to fight against ChatGPT directly, ChatGPT 3.5, I should say. And we are not even going to rely on the NLI classifier. Because some people, when we write this paper, it's like, you rely on some supervised classifier, that's dirty. I don't know what that means, but Some people seem to think everything has to be like totally self-supervised. Somehow RLHF is okay. I don't know why that's okay, but some people seem to think that they have this expectation about what's beautiful and what's not. So we wanted to see whether we just get rid of that supervised component altogether. So how on the earth is that possible? There's something called information theory that it's information theory inspired formulation. That's a fancy way of saying what we do, which is basically mutual information rewritten such that we can now measure the saliency and faithfulness and brevity of summarization. You can look at the paper for further details, but it kind of like we just shuffle around point-wise mutual information into different equations. And then we can now use these equations as filters instead of Intel-Monte classifier. Now we have just like off-the-shelf language model-based quantification of saliency and faithfulness and brevity. Okay, so we do that, and the rest is the same story, which is that in our case, we started with the small model as Pythia because that's better than GPT-2. And then we overgenerate. And then we filter using these self-supervised critics based on basically rewritten point-wise mutual information. And then we take these iterations to train the small model with better data. So after some iterations, we now have InfoSum data set, which has like over 4 million high-quality document summary pairs. And then for the fun of it, we trained the final student model so tiny, it's not even a billion, it's only 500 million model. And then we compared against ChatGPT 3.5. That's 200 times larger. So the conclusion is that we were able to beat it all. And not only that, we were on par with the ChatGPT, but we wanted to beat it. So in order to beat it, we decided we're going to also try with the best of 10 re-ranking. But we also let ChatGPT to do also best of 10 re-ranking using their own probability score, but we do better than that. We can also do controlled summarization, for which ChatGPT is not as good, and then we can do better than ChatGPT. Okay, so to summarize, I just demonstrated that an example of doing things that seemed impossible but potentially possible. But really the reason why we wanted to study summarization is because there's these underlying research questions, including learning to abstract. Currently, right now, like a lot of people just try to make the model larger and larger, and these models are able to look at very, very long context as is. It's like verbatim memorization of the whole context in their memory. Humans, on the other hand, you and I cannot possibly memorize anything verbatim more than a sentence, right? But you don't have any problem understanding my talk so far, and you have a good mental memory of what I said, but you just instantaneously abstract away everything you read and you hear. We were wondering whether we should do more aggressive research about learning to abstract, and this was one step toward that. And in doing so, we wanted to see whether we can learn without a lot of human written text, because at the end of the day, AI today is powerful because of us, because of our data, that the human intelligence that was reflected in the internet data. But the thing about human intelligence is that, well, we started from zero and then we came this far. And we're wondering whether we could start with less data, not zero data, but less data, and see whether we can close the gap. Okay, so I have another mission impossible to share with you, which is Infinigram, with my student Gary and others. I don't know if he's around here. But why is this mission impossible is because, first of all, we wanted to make n-gram language models relevant. I don't know how many of you hear this word anymore, n-grams. It's not cool anymore. Like NLP class these days, like they threw out n-grams out of the class material even. Okay, so where n infinity, by the way, this sounds hard, over a web course corpus with more than 3 trillion tokens, and then n-gram lookup speed should be less than 100 milliseconds, and then without GPUs. What are you talking about? Without GPUs. We're 2024 right now. Okay, so if you were to, hypothetically index 5 trillion tokens with infinitely, just arbitrary length of n-grams, then there may be 2 quadrillion unique n-grams to index. And that's too many. And hypothetically, that might, like roughly speaking, require 32 petabytes of hard disk that we don't have. So this just seems impossible. What was the largest language model, n-gram language model built prior to our work is from Jeff Dean, the keynote speaker here, who did this work 17 years ago, 2007. So this is really, not the current day fashionable stuff anymore. But back then, they did look at only n-grams less than 5 grams because, anything beyond that blows up too fast. When they indexed the 2 trillion tokens, they ended up having 300 billion unique n-grams. So you see how things blow up really, really fast. Okay. So we have this live demo right now. If you want to check it out, infinigram.io/demo. It's super fast, so you can go and look up stuff as you wish. So here's one example that, we tried. So we found, after building this infinigram, we found that there's some weird words on the internet. I don't know how to pronounce this, but it's like 45 letters with 17 tokens. You can search this on our infinigram web demo, and the latency of getting that number is 5 milliseconds. And then it also gives you how it's tokenized. If you want, you can also find documents where this did appear, some sample of documents. You can do a lot of things. So this appeared this many times on one of the corpus that I searched. You can also look at, what if you give you give like n-gram sequence, like actions speak louder than what, and then get this distribution of what comes next. So these things are also very fast, like 3 milliseconds latency. Okay, so what did we do? You might wonder. There's something called the suffix array that some algorithm classes teach, I guess. It's one slide that I'm going to show you. So suppose there's text corpus. And so we're going to build this suffix array. So this text corpus, as you see, has like a token location ID that increases. And then suffix array is randomly appearing numbers that basically points to where things are. So this suffix array is an array. Basically, it's demonstrating these n-grams of arbitrary length. Because it's arbitrarily long, I'm showing you only the suffix starting that, potentially infinitely long n-grams. And we surely don't store this part, but just like these numbers are what matters. So the rank means just like the original sequence that you see above. And then pointer is where these unique different n-grams start in your corpus. Okay, so for example, if you want to count University of, you want to look at all the n-grams that starts with University of. And then so you go to those positions, and then you find where these suffix array pointers point to, and then you can find the exact count super fast. So that's sort of the idea. And then how efficient is this, especially with the C++, by the way. You cannot do this with Java or Python. The kind of efficiency is coming from C++. So indexing only $500, inference $600 per month. Not bad, I would say. And you can do a lot of different kinds of inferences, usually way less than 100 milliseconds of time. You can also use our n-grams in order to enhance your favorite large language model's perplexity by taking interpolation between your neural language models and our infinigram. So here, for example, we were able to enhance over Llama 270B model on the bottom. And in general, we were able to get perplexity reduction, like even for the last low, about 18% or 19%. Okay, so you can also access this through APIs. If you don't want a web interface, but you want to code this up really fast, over 2 months of time, we got like 60 million API calls already. So you're welcome to use this. I think a lot of people are doing creative stuff. I'm also doing something with it, really fun stuff. Okay, so last I am going to talk about some paradoxes. So I'm going to talk about two paradoxes, common sense paradox, and then generative AI paradox. So my talk wouldn't be complete without a few words on common sense, because I was starting working on it 7 years ago. When people told me that it's a research topic of the 70s and 80s, I shouldn't work on it because it will never work. In fact, don't even say the word to be taken seriously. I managed to get a tenure regardless at UW. So nice of them. Now 2024, people tell me don't work on it because ChatGPT almost solved it all. And it does look that way, doesn't it? Because this Twitter announcement of your LLMs always include common sense. And it includes things like HelloSwag, Winogrande, which I also noticed in earlier morning session. People like these data sets. And Jeff Dean, his tweet also includes some common sense benchmark highlighted on the bottom. And then if you open their actual tech report, there are a lot more reported. Looks like, yeah, common sense is going really well. But we actually looked at some of these a little bit more carefully, and it's actually really good, but not exactly at the human level, first of all. But still, their performance is close to human level. But the truth is, here's the truth. There are actually a lot of other newer common sense benchmarks that my group also have generated, but they usually don't appear in this kind of a tech document because the numbers look not as exciting. I'll show you some example, but there's a bit of a debate about whether theory of mind may have spontaneously emerged in large language models or not, because Stanford professor, for example, tried 20 different complex examples, and then GPT-3 got everything right. So, looks like theory of mind must have emerged. And then there were some other counterpoints that, including my own paper, that says otherwise. So in case you kind of forgot what theory of mind is, here's one very representative example. Alice and Bob saw apples on the table in the kitchen. Alice left the kitchen, and then Bob moved the apples to the cabinet. Now you ask, where would Bob think that Alice will look for the apples? So 2 years ago, GPT-3 used to be not very good at this. So he said in the cabinet, and that's because there's a recency bias. It just picks the location that was mentioned the most recently. But that's so 2022. As of last year, it's already fixed. GPT-4 answers this correctly. So I had a hunch. What if I rotate the second sentence and third sentence? Now it says, on the table still. It kind of learned this trick question that people usually ask a trick question, but not the other way. So best strategy is to stick with the first location. But this is last year. So, people tell me that, well, this year, this is all correct. So as of a few days ago, I checked this again. The same question, it got wrong. So I was like, no way. Like, this is like, I was not believing that this is wrong. I mean, cannot be wrong, I thought. And then I remembered, I have this system prompt that does a pep talk. I'm going to show you what that is. Encourages step-by-step reasoning. So I removed it and tried again, and without system prompt, it does give me correct answer. So depending on what you try, I'm showing you both because usually what happens is that if I only show the incorrect example, later people, chase after me that how could you possibly, because I just tried and it did work. So depending on how exactly you ask, with or without system prompt, you may get different results. So the reason why I had this system prompt turned on is because of Jeremy Howard, who said, if you use that prompt, it usually works better. And I agree, usually it does work better, but it's not guaranteed. So what does it say? You are an autoregressive language model that has been fine-tuned with instruction-tuned LLHF. You carefully provide accurate, factual, thoughtful, nuanced answers and are brilliant at reasoning. Yada, yada. So, you have to do pep talk, and usually it does do better. But why did it not always work has to do with this problem. So this is our ICLR paper that we presented just last week. So basically, your LLMs, favorite LLMs, can be strikingly sensitive to superior features in the prompt design. Or how I learned to start worrying about prompt formatting, because depending on how you do it, you can get wildly different results, like even spacing can sometimes, or some special symbols or new line characters. Okay, so we have another related paper that looked at theory of mind examples with varying configurations. So, instead of 2 location, 2 people, we, for example, had 3 people, 3 containers, or 3 locations. So this was designed before ChatGPT changed the world. So this was with GPT-3 still. And then we tested on GPT-4, and it so happens that GPT-4 is sometimes good, but mostly not as impressive as you would have imagined. But when I show this kind of example, some people tell me that, hey, who asked this kind of question at all? And even I cannot do this, people tell me. So then we did the following work. Okay, if you really want to degrade yourself, that you cannot do it. And by the way, we did do human evaluation on this, and the crowd workers were able to do this. So some other people out there can do that if you cannot do that. Okay, but anyway, so Phantom. The truth about theory of mind, by the way, is that the examples in the literature of psychology is sort of like artificial, in the sense that who asked like a story where you went somewhere else and then like somebody moved to something. Nobody actually talk about theory of mind that way. The real life scenario of theory of mind should be in a conversation. So we had this hunch that the reason why ChatGPT is good at theory of mind benchmarks is because that kind of examples are mentioned in the psychology literature. But what if you ask a theory of mind questions on a conversational setting? It's slightly different. But for you, this is the natural way for you to reason about theory of mind all the time. And not only that, we designed 3 different ways of asking the same question, which has to do with either asking belief or answerability question or info accessibility. These are like minor differences of the same question asked differently. And here's the result we got. So gray is human performance. So you see that these are like different types of problem formulation. It's the same problem formulated differently. And humans are good at all 3, such that if you say this upper left corner says, you have to be correct on all 3, then you get the full score. And as a human, it's easy to get correct on all 3. But with ChatGPT, weirdly enough, it's not as good at this than this bottom 2. And that's because these are asked in a different style. It's like same content, but asked differently, and the performance drops, and we see sharp differences. So I wonder when we're going to see this benchmark in the LLM release tweet. Okay, so I'm going to skip over some of the details, but basically we find that, again, LLMs are tricked by their own use of the shortcuts. Chain of thought doesn't help. In this case, it actually worsens the performance. Let me think. I think I'm not going to do this part. Let me skip over and just go right here. Okay, so I'm going to share, finally, the common sense paradox. So I'm going to dare say the following 4 statements are all true. Common sense is trivial for humans, harder for machines. Among humans, common sense is not so common, said Voltaire lots of years ago, and it's still true. And in fact, even among scientists, I sometimes wonder about that. LLMs do require a vast amount of common sense knowledge, yet in some ways, I think Jan LeCun has some point that, there's, in some aspect, AI is worse than a dog. Weirdly enough, these are all simultaneously true in different ways. Okay, generative AI paradox. What it can create, it may not understand. Also presented at ICLR last week. So the paper gives you a little bit more like a formal definition of what we're talking about, but the hand-wavy definition of what we're talking about is that the generative models, for generative models, hard may be easy and easy may be hard. And here, hard is generation and easy is understanding. So this is a little bit reversed compared to human intelligence, where in general, we find understanding is easier than generation, such that, you can, or I can understand New York Times articles. I cannot generate that, elaborate, fluent writing style of New York Times articles. So whereas generative model, AI models, things seem a bit different. And that's true even for the vision models. So you ask DALL-E 3 to draw a photorealistic astronaut doing a plank on a table. I don't know why somebody wants to ask this, but Peter, the lead author, asked. So I cannot possibly draw any of this. That's beyond my capability. But if you really stare at this, 3 are wrong, 1 is correct. And for human, this is easy to tell that, oh, the correct one is that. So as a human, by the way, when you use DALL-E 3, it's pretty common that DALL-E 3 gives you lots of examples, and then you as a human does that hard selection job. And then people kind of ignore that part, and it's like, oh, generative AI is so good. Yeah, it's very good, but you're also very good. We also tested this with large language models like GPT-4, where we asked it to generate a short story, 2 paragraphs. So we asked it, write a 2-paragraph story about 3 people building a house. It's a very simple story that it did generate. And it's the story basically talks about trying different sketches and finally going with one sketch, and it worked well. So we asked, hey, how many total designs were sketched in your story? And he says, only 1 sketch, which is not true. It did talk about itself multiple sketches. So I'm not saying, by the way, in general, understanding is top quality. You ask, these kind of questions. Usually, ChatGPT is very, very good at understanding this kind of a task and give you the correct answer. It's just that compared to humans, we found that sometimes it's strikingly not able to do this. So this is all relative. But the reason why we wanted to do this study is because, a lot of the times, we see ChatGPT doing something really well. We're so impressed by it. We project ourselves onto ChatGPT or generative AI in general, and then expect that it's good at everything else. But that doesn't work because these models are very different from us. It does share a lot of commonalities, but there are also a lot of differences. So as a scientist, I think we need to be a little bit more precise about the differences as well. Okay, so in the paper, we also talk about how there's a difference between generative evaluation versus discriminative evaluation, where, as a human, you will find the multiple choice questions is sometimes easier than open-ended answer generation, where you may not recall the correct answer. Whereas we find that it's a little bit reversed with generative AI. There are some related work, such as the generative AI paradox in evaluation. What it can solve, it may not be able to evaluate. We have this paper from ICLR last week as well, where we tested the inductive reasoning capabilities of large language models, and we found that ChatGPT is better at generating inductive hypotheses as opposed to validating inductive hypotheses. Again, this is reversed for humans. We're better at validating than generating hypotheses. There's a really fun paper that I really like, the reversal curves. So in this case, LLMs trained on A's B failed to learn B's A. So some example here is let's see. Who is Tom Cruise's mother? So on the bottom of the page, who is Tom Cruise's mother? Mary Lee Pfeiffer. So it may not we may not be able to reverse this factual statement correctly, regardless of the size of the model. So there are some problems that we need to recognize. Okay, I'll share some short concluding remarks. Long time ago, when student Max Planck considered to do PhD in physics, the professor Philip von Joly said, I'll advise not, because in this field, almost everything is already discovered, and all that remains is to fill in a few unimportant holes. Student said, I don't wish to discover new things. I only want to understand some known fundamentals, and went ahead and created this whole new field of quantum physics, because it turns out there were actually a lot of unknown things that people just were not aware. back then. So it may be that, right now we feel like we understand everything about transformers because we know how to write the equations. But it may be that we're just really opening this a can of new problems, lots of exciting problems to study. And perhaps we need to study these LLMs as it's similar to how, the fact that humans know how to give birth to another human being doesn't mean that we understand everything about the human body or mental states, right? So similarly, maybe that we just have a lot of new problems to think about. And here's one shout out of a recent paper that identifies 18 foundational challenges and 200 concrete research questions. So, this is probably tip of the iceberg. Lots of scientific problems to think about. Okay, so another takeaway is the alternative paradigm. Although these extreme scale LLMs are truly fascinating, there's something fundamentally odd about how the corner cases are fixed today. And also, I'm counting on the fact that whenever somebody invented something in the history of humanity, usually there's something better. Like, the first personal computer was not small enough, and the first personal cell phone was not as impressive. So I'm hoping that somebody figures something out, but I'm a little worried that a lot of people just end up doing the same thing right now. But it may be that there are actually multiple paths to reach, strong AI or AGI even. It's just that we may or may not find them, but the truth might be there. And scale is all you need. It might be just one of those recipes. And all these different routes might lead to different intelligences with different strengths and weaknesses, such that one doesn't necessarily dominate the other. It's a hypothesis. I'm just speculating. But I'm really hoping that people try different ideas other than just, single-handedly scaling things up, because this scale-based approach inevitably suffer from these blind spots. Whenever something is missing from the training data or pre-training data or RLHF data, they keep suffering. So I hope that we try other routes as well. Thank you.
Hi, thank you for the very insightful talk. I think it's worth understanding why LLMs are not good at various tasks, like including mathematics, theory of minds, and writing a new story. But what do you think the single most critical ability that current LLMs are missing that people really want at the current moment? So, I play with ChatGPT at the first time because it's interesting, but these days I'm only using the Copilot to assist my coding. So I'm really curious about what the people really want, not just about the benchmarking in the academic perspectives.
So what's fundamentally lacking in the large language models? In my mind, it's not really learning concepts really thoroughly well, which may be the source of the failure for some of these commonsensical questions compared to how these are much easier for humans. I actually have really a lot of examples that I didn't put here, but it's really fascinating how what's easy and what's hard can be different. But I don't really have a good a solution around this. To be honest, I'm just complaining about the fact that scale-based method does seem to have concerns, and maybe we can try to think about alternative routes. But maybe one thing I can mention is that if you think about how human babies learn, imagine teaching your baby with internet data, broadband, lots of data, sequentially, no interactions, by the way, just feed everything in sequence. The baby doesn't have any saying in going back to the previous story and rereading and asking questions, nothing allowed. So the current way of training LLMs are super passive. And then the model doesn't really have epistemic awareness about what it doesn't know. It's not really trained to think about it. And I do wonder whether the current recipe that is passive by design is part of the problem.
Okay, another question here. Thank you for this amazing talk. I have a series of questions, so get ready. The first is, when you do the multiplication, did you ask nicely and politely to GPT-4? No, sorry. The real question is, perhaps more relevant, is when are we going to see new models coming? Because I believe system folks here are bored with transformers already. And the follow-up question is more related to maybe NLP. So I have trouble understanding, let's say, if we were trying to have this ability to reason and to infer, why are we doing token by token? Because that's definitely not what I'm thinking. So if you're saying if we can do the next idea prediction, somehow use some sort of latent there, then maybe I could be persuaded that, oh, sometimes this model can have reasonable string result. But for now, it's token by token. Maybe it's using a different way of inferring, but that's intuitively not, I think, what we are doing at this point. So,
yeah, a lot of great questions. Thank you. First of all, we're not that polite. Transformer, I don't know if, people are trying different architectures, but it's not entirely clear in terms of gaining certain kinds of a scale, whether we have a clear idea yet. But the impossible distillation that I demonstrated was also based on transformers. So it's also possible that the architecture can be transformers. It's just that learning objective or running recipe can be different. And, in my mind, a lot of people just, maybe just change out the neural network architecture, but it may be that there are other things surrounding it that could also change, such as should we really try to predict the next token? Like I said, maybe have the next idea, but also should we allow it to reflect on what it did learn and think about, reflect on what it has learned. And in some ways, I would argue that, what we were doing here with impossible distillation is a little bit like letting the language model to reflect on, how to summarize abstract away things, and then trying to update the parameter on its own explorative thoughts on summarization. So actually, this one was also going into that kind of a direction, like seeking alternative training method. Okay, your last question was about tokenization. Yeah, so I agree that it's a super awkward and it's a weird thing we're doing. I mean, if you really want to be like a human, then maybe we should start with the pixels and then go directly at, I don't know, but yeah.
Okay, another question? Yeah, so first, thanks for the great talk. I have 3 questions. The first question is, do you think so you mentioned for LLM, easy is hard, hard is easy. Do you think it is because LLM is like a curse of LLM because it's too complex? So people really, I don't think people understand LLM, especially from mathematically. Yeah, people don't understand it. Do you think if it's because people don't really understand it? So that's why it can't understand, the LLM can't understand common sense. The other question is, do you think the current transformer-based solution for LLM will really solve the common sense problem, or we may need to adopt a new technique to solve this problem? Yeah, thanks.
Yeah, so the current way of, by the way, when ChatGPT first came out, I was really impressed by, I should back off a little bit. When GPT-4 came out, I was very impressed by its common sense capabilities compared to ChatGPT. So there was a sudden major jump from ChatGPT 3.5 to 4 when it first rolled up, by the way, because now they updated all these model varieties, so they became similarly good at this point. But so, there's 2 possibilities. One is that, maybe it's coming from pre-training somehow, or it's coming from RLHF. I have my own speculation, but of course this is like a closed model, so nobody knows what exactly happened there. But my intuition is that in general, based on what I have tried so far, when it works, it has something to do with whether there was internet data or not. So the truth about common sense benchmark is that, it's part of internet data. Even if they avoided using them during pre-training, which I believe that they have had, the thing is, through RLHF, people ask a lot of common sense questions to the API calls, and those questions probably leaked into that RLHF alignment process. So, and also, whenever I give public talks, and then an example becomes super popular, in a month or so, it's fixed. And then, I try different variety and it has not been fixed. I've been going through this a lot. But if I personally try at home, usually they don't fix it. So I think it correlates with, an example becoming popular. Then what happens is that nobody believes that ChatGPT would have made a mistake. So you all go home and try. And probably that becomes like important API calls that they take a look. I suspect, I don't know for sure. Maybe they didn't do anything and magically everything just got better. I don't know. But that doesn't seem like correct way of doing this because you and I didn't need to RLHF ourselves with the common sense. So I think just like the universe has the solution to this, but we don't know what that is.
Hi, thank you for the very interesting talk. I want to know if you've seen ChatGPT 4.0 and given the issues that you brought up today, if you had any thoughts on where it's moving and the direction that ChatGPT is moving into.
Well, personally, I'm biased because one of the presenters was my former student, Rowan Zellers. So I was like, super psyched to see him giving the demo. So proud of him. Well, I think it's super impressive and very creative work. But the demo itself looked great. I'm pretty sure that, if you poke it around, it's going to make a mistake again. But it might have really good use cases. I mentioned especially like real-time translation seems just amazing. Even if it's not fully correct, it's better than nothing. So I rely on already Google Translate quite a bit when I go to foreign countries, and it would be wonderful to have real-time audio-based translation among others. So it's exciting. But that kind of programs, I imagine, will also have certain kinds of societal implications, and we don't yet understand what that is. So that also just like opens a lot of new problems to think about.
Thank you so much for the great talk. I think my question might come from a place of bias, and it's more of a philosophical question than a direct current research question. My background was in biology, and I find that we have kind of drifted away from the idea of neuron and trying to mimic biological neurons. Do you suspect, as you said, the answer might be in nature, do you suspect there would be renewed interest in that area as we continue to see more research in biology? Especially there was a picture of brain neurons and the dense, like how densely packed they are in terms of connections.
Yeah, that's a great question. So I personally think that there might be multiple entirely different solutions to amazing AI or intelligences, like it's plural. And so human intelligence is one version of it. It may be that for computer to be super intelligent, it may not have to be biological. It may not have to be similar to the way that human neurons are connected due to the fact that these machines will not have the kind of embodiment that humans do have. So they don't really learn from the embodied experience, which is major disadvantage for them. And in order to overcome that, maybe their advantage should be about the data. So, it might also be that there's like some other variant of artificial intelligence that somehow is like a hybrid solution between the two that might turn out to be more robust at really understanding how the world works. Yeah.
All right, one last question back here.
Hi, my name is Kimbo. Thank you for the really insightful talk. So my question is, wonder what's your view on mechanistic interpretability and like solving synthetic tasks to improve models? Do you think that's one of the ways that you mentioned of doing the science of LLMs? Thank you.
Yeah, I really appreciate any interpretability work, including mechanistic interpretability. I understand that, there's a bit of arguments about, whether there's limit as to how much you can actually interpret it that way, etc. But still, I find that the insights we find from that sort of research is helpful. In fact, maybe this paper by Tom Michel that looks at the internal state of LLMs to know when it's not telling you the truth is going into that direction. It's not as mechanistic interpretability per se, but this sort of knowledge could potentially be helpful in at least probing the language models, if not even enhancing its behaviors based on these probed signals. But in general, these are a bit of a patch-up way of improving the problems of LLMs, but still it's helpful, and I generally very much endorse any effort in this space.
Okay, with that, let's thank Yejin again for a fabulous talk.